Let's start the class. So today what I am going to discuss with you is the basic principles, the steps and the process chain of rapid prototyping, and what are the basic advantages of rapid prototyping system. So what is the basic principle of rapid prototyping? The idea is pretty simple actually. This is a bed. This is the bed that you have got. Now on this bed, you are trying to create an object. Now this axis is called as the x-axis and this axis is called as the y-axis. And the part is going to be fabricated in the third axis. The part is going to be fabricated in the third axis that is called as the z-axis. Okay. So when you plot something on xy axis, suppose if I plot a circle on xy axis, what does it give me? What does it give me? It gives me a 2D contour. Along the x plane and y plane, what it is giving me? It is giving me a 2D contour. Okay. So how does the third dimension come into picture? When we deposit layer after layer of material, that layer thickness, now if you see from the side, what you will observe is something like this. Something like this. So this is the layer thickness that you are talking about. So if you look from top, this is the view you are getting. And if you look from the side, this is the view you are going to get. So this is the basic principle of rapid prototyping. Okay? So in rapid prototyping, what basically happens is the deposition happens along the Z direction. The deposition is going to happen along the Z direction. Okay? So the object is going to be deposited along the Z axis. Now, the layers are going to be contoured in xy plane. So xy plane is going to basically give me a contour of the geometry that is going to be fabricated along xy plane. And the third dimension, that is the z dimension, is going to give me the stacking of layers. So this axis is the z axis and this axis is actually giving me the stacking of the layers. Therefore, the prototype is built in contour form in xy plane, and the height of the layer thickness gives me the z axis. So this is how the parts are fabricated in additive manufacturing or rapid prototyping system. Now the information that is generated, basically generated over here is depicted in two forms, or it can be stored in two forms. The first is the mathematical layer information. And second is the generation of the physical layer model. Now, how are we doing this? Assume this is your contour plane, this is your x plane, and this is going to be your y plane. And this is the geometry that you have fabricated. ठीक है? और इसके अंदर आपने हैचिंग कर दी है. ठीक है? ये जो आपने कर्व बनाया, बाउंड्री कर्व जिसको हम कहते हैं, ये जो आपने कर्व बनाया, बाउंड्री कर्व, ये क्या है बेसिकली? कोई बता सकता है मुझे? ये है क्या? है? ये है क्या? इसको रिप्रेजेंट कैसे करेंगे? चलिए और सिंपल क्वेश्चन पूछता हूं, इसको रिप्रेजेंट कैसे करेंगे?
So, is it a circle?
It's a curve. I am saying it's a curve. A circle is also a closed curve. ठीक है ना?
हाँ, पैरामीट्रिक इक्वेशन यूज कर सकते हैं.
Very good. That is what I wanted. एक पैरामीट्रिक इक्वेशन से, ठीक है? ये जो पैरामीट्रिक इक्वेशन है, ये क्या है बेसिकली?
x square plus y square equal to r square और z square.
हाँ, मतलब कुछ भी आप नाम दे दीजिए.
Yes.
ये क्या है? ये क्या है? ये है
मैथमेटिकल लेयर फॉर्मेशन. यस.
ठीक है?
यस.
अब आता है सेकंड पार्ट. सेकंड पार्ट को हम देखेंगे साइड से. ठीक है? ये तो टॉप से था, अब हम देख रहे हैं साइड से. ये आपका बेड है. ठीक है? जिसको हम ये कह रहे हैं बेड है, ये आपका बेड है. इसके ऊपर आपने एक लेयर बनाई. ठीक, लेयर की एक कॉन्टूर है वो ये रही, लेयर की जो कॉन्टूर थी वो यहां पर है, ये क्या है, लेयर हाइट। तो एक पूरी लेयर बनाने के लिए, एक पूरी लेयर डेवलप करने के लिए मुझे क्या क्या इंफॉर्मेशन चाहिए, व्हाट इज द इंफॉर्मेशन दैट इज नीडेड टू क्रिएट वन लेयर।
सर कर्व की पैरामीट्रिक इक्वेशन और थिकनेस कितना मटेरियल का चाहिए मतलब?
तो हमको बेसिकली इसको अगर हम 1 कहते हैं ये, और इसको अगर हम 2 कहते हैं, तो व्हाट इज द लेयर इंफॉर्मेशन कंसिस्टिंग 1 + 2। So whenever you see the data, not the physical form, but the data form of additive manufacturing CAD model, the CAD model is actually containing two informations. The first information is the parametric equation of each and every individual layer. Suppose this is only for one layer. Suppose if it has got 5 layers, है ना? So every layer, every individual layer, this is my first, this is first layer, this is second, this is third, this is fourth, this is fifth. So every individual layer is going to contain these two informations. And the best part is this information is a discrete information. It is a discrete information. It is not going to be similar for layer 1 and layer 2. It is not going to be similar. Why? Because the parametric equation will change. The data points of the parametric equation will change. So every layer information that is developed or processed in additive manufacturing system or rapid prototyping system is a discrete information. So if you change this information, what will happen? If you change this discrete information, what will happen? Anybody? If I change the discrete information, what happens? कोई बता सकता है?
Shape and size will change, sir.
Of what?
Layers vary करेगी.
Layers will start to vary.
Yes, sir.
The layer information will change. As a result, your individual layers can also be varied in additive manufacturing. That is the best advantage that you get as compared to any other system. If you change either the mathematical information, or the physical information, you can change that individual layer without affecting the other layers, So this is the advantage of additive manufacturing or rapid prototyping. So what is the basic principle of rapid prototyping? It can be explained in these 6 steps. The steps actually start from here. This is the cross flow. This is the cross flow. So first what we do is we generate a CAD model. The first thing that we do is we generate the CAD model. Then what we do is in between, after generating the CAD models, we tessellate. We tessellate the CAD model. What is tessellation? I'll explain in the next subsequent slides. So once we tessellate these models, we send it to the other software which does the slicing of the CAD model. Now, when you slice a CAD model, it is as good as defining the layer thickness. So first step is to create a CAD model. Then intermediate step is to tessellate that CAD model. After tessellation, the slicing happens. Once the slicing happens, look at the corners. So the corners are something like this. There is a sloping edge on the corners. and it is very difficult to develop a sloping edged equipment. So what happens is the software by default cuts out the sweeping edge and converts it into flat edges. That is what we call as the squaring edges. Now, once the edges have been squared, this will be sent to the RP machine for fabrication. And what will happen is the stacking and pasting of layers will happen inside the RP machine. The stacking and pasting of layers will happen inside the RP machine. How this pasting is taking place? This pasting is basically taking place due to heat plus molecular bonding. Now, once this whole stack has been pasted together, what you get is a physical prototype. This is actually the output from the RP machine. This is going to be the output from the RP machine. Now, once you get an output from an RP machine, what you observe over here is this. What is this? Can you see this effect?
Yes.
Can you relate it to something that you have seen in your day-to-day life?
Stairs.
Stairs, so
Yes, this is called as the staircasing effect. That is the name of this effect, staircasing effect. Now tell me what will happen if I take a probe. If I take a probe and move that probe across this direction, what will happen over here? What will happen over here? What will you observe or what will you feel? Let's assume the probe is your finger. Let's assume the probe is your finger. You rub your finger across this direction. What will you feel?
so roughness or maybe a crest.
Excellent. You will observe a deficiency in surface finish. We don't call it roughness over here. We call it surface finish.
Yes.
So what we observe is that the surface finish over here and surface finish in the physical prototype is going to be different. ये CAD मॉडल है. CAD मॉडल को तो आप कितना भी स्मूथ कर सकते हो ना,
Yes, sir.
पर ये तो फिजिकल प्रोटोटाइप है. इस फिजिकल प्रोटोटाइप में ये जो प्रोफाइल है, इस प्रोफाइल में सरफेस रफनेस डेवलप होने का रीजन क्या है?
सर वो जो अप्रोक्सीमेशन हम लोग ने स्क्वायरिंग एजेस ऑफ मॉडल में लिया था कि हमने वो
नहीं, आंसर स्लाइड पे लिखा हुआ है. आंसर स्लाइड पे लिखा हुआ है.
लेयर थिकनेस.
डेफिनेटली. अगर अभी आपने पीछे वाली स्लाइड को ध्यान से नहीं सुना है, this T is actually going to define the contour height, and that is the reason why you are getting this staircase. Understood? So layer thickness becomes one of the most important aspects in additive manufacturing or rapid prototyping when you are manufacturing a product. Always remember that. Now, suppose you want to reduce this staircasing effect. What will you do?
सर स्लाइसिंग जो हम लोग ने करी है वो
एक एक करके सारे एक साथ में बोलो. हाँ.
पेशेंस को वेरी करेगा सर, पैरामीट्रिक पेशेंस.
कौन सा
वही जो आपने प्रीवियस स्लाइड में बताया था कि लेयर्स को फिर वेरी हो जाएगी सर, मतलब वो फिर स्टेयरकेस नहीं बनेगा सर वो.
हाँ, तो स्टेयरकेस को वेरी कम करने के लिए कौन सा पैरामीटर यूज कर रहा है, मैथमेटिकल की फिजिकल?
मैथमेटिकल करेंगे सर शायद.
गलत. फिजिकल पैरामीटर चेंज करना पड़ेगा. This layer thickness has to be minimized. This layer thickness has to be minimized. The stair casing effect is not being generated due to mathematical information. It is being developed due to this layering process. ठीक है, तो लेयरिंग प्रोसेस का सबसे प्राइमरी पैरामीटर इज T, that is layer thickness. So if you want to have a fine surface finish, देखो, one thing keep in mind, always keep in mind, surface roughness cannot be eliminated in this process. Additive manufacturing process, surface finish is always going to be compromised. But in order to attain a very good surface finish, what you can definitely do is you can take this layer thickness to a minimum value. What happens when you take it to a minimum value? I'll explain it when we will discuss the processes. Okay, there are repercussions for that also.
So operation time बढ़ नहीं जाएगा इस केस में?
100%. That's what I'm saying. The repercussions I'll discuss not today, because today I'm just telling you the basic concept. Okay, so I'll discuss the physical parameters and all these things later on. Okay, so now let us come back. Now you have a physical prototype, and that physical prototype that you can observe has a surface finish problem. So what you can do is you can go for post-processing. So once you do post-processing, you get the finished physical prototype, then you check it. If it is okay, then it is sent somewhere else. If it is not okay, you go back to the CAD model. So this is the basic principle of additive manufacturing. You prepare a CAD model, you tessellate it, you slice it, you square off the edges, then you send it to an RP machine. RP machine fabricates it by stacking and pasting layers. You get a physical prototype, and the physical prototype is post-processed. After post-processing, you check the finished prototype. If it suits your application, it's okay. If it doesn't suit your application, it's a waste. You throw that away, go back to your CAD model and reprocess. Am I clear?
Yes, sir.
Good. So what are the basic steps in additive manufacturing? So basic steps are basically defined by 4 major steps. The first major step is what I have been telling you since the first class. I need a CAD model. The first thing is I need a CAD model. Okay. Once a CAD model is ready, we convert that CAD model into STL format. STL format. Now what is STL for? STL stands for
Stereolithography.
stereolithography. Okay, this is the format. How this came into picture, I'll just give you a very brief idea. The first commercial industrial process of rapid prototyping was called as stereolithography, and it used liquid resin to develop a prototype. So the format that came along with that machine got to be named as stereolithography format, and the short form for that was STL format. So that is how it started. It's a very simple format, so it became a de facto standard for all the machines and softwares which are related to additive manufacturing to possess this feature. Now, once the STL file has been generated, the STL file is then transferred for cutting into thin layers, and then it is transferred to the machine. The machine is going to fabricate it one on top of the other, and you get a physical prototype. So the most important aspect is you create a CAD model and you convert the CAD model into an STL file. No other, generally, most of the softwares don't accept any other format also. So always remember, when you are creating a model for additive manufacturing, you need to convert that .prt file or whatever file that you are creating into .stl format. Okay? Now this is the process chain. The process chain is somewhat similar to the methodology that I discussed earlier also. It is very much similar. But here I'm going to explain something, what is tessellation also over here. So the first thing is you create a geometric model, that is your CAD model. That is the first thing, that you create a CAD model. Now let us assume you created this CAD model of a cylinder. So this is a cylinder that has been created. Now if you look at the cylinder very carefully, what do you observe? How is a cylinder going to be defined? Now can you define a cylinder for me? How a cylinder is going to be defined? Because now what we are talking about is not entities, but we are talking about surfaces. We are talking about surfaces. So how will you define a cylinder? Or how many surfaces will a cylinder possess? चलिए और भी सिंपल पूछ रहा हूं. How many surfaces will the cylinder possess?
सर कर्व सरफेस एरियाज जो हैं उसके बॉडी का
चलो और नहीं मोटा मोटा बताओ अभी, इतना डिफाइंड डिटेल में नहीं.
सर 3
कौन कौन से?
सर बॉटम टॉप और सर जो ओवरऑल सर एरिया
बॉटम,
टॉप
एंड
और सर
साइड सरफेस.
सर
साइड सरफेस. ठीक. अच्छा, बॉटम क्या है? एक सर्कुलर. टॉप क्या है? एक सर्कुलर. और साइड क्या है? एक ट्राइंगुलर. रेक्टेंगुलर. ठीक. इसकी एक अपनी मैथमेटिकल इंफॉर्मेशन होगी, इसको कहते हैं मैथ 1. इसकी एक अलग होगी मैथ 2, और इसकी एक अलग होगी मैथ 3. नंबर ऑफ पॉइंट्स कितने होंगे इसमें? इन्यूमरेबल. हम गिन ही नहीं पाएंगे शायद. तो जो मैथमेटिकल इंफॉर्मेशन, आई एम जस्ट गोइंग बैक वंस अगेन, ये जो मैथमेटिकल इंफॉर्मेशन है ये क्या हो जाएगी? बहुत ज्यादा कॉम्प्लेक्स हो जाएगी. क्यों? क्योंकि इसके पेरिफेरी पे, इस वाली पेरिफेरी पे, रेक्टेंगल की इस पेरिफेरी पे जो पॉइंट्स है वो सर्किल के पेरिफेरी के पॉइंट्स के साथ मैच करेंगे. तो आपको ये चूज करना पड़ेगा कि जो पेरिफेरी वाले पॉइंट्स हैं वो इस पे रहेंगे कि इस पे रहेंगे. सिमिलरली बॉटम पेरिफेरी के जो पॉइंट्स हैं वो इस बॉटम सर्किल के साथ रहेंगे. तो अब आपको ये चूज करना है कि वो पेरिफेरी के पॉइंट सर्किल पे रहेंगे कि रेक्टेंगल के साइड में रहेंगे. सो कितनी सारी इंफॉर्मेशन आप जनरेट कर रहे हैं, और इस इंफॉर्मेशन को आपको स्टोर करके भी रखना है. That is why tessellation came into picture. What is tessellation? Any idea?
Is it like discretization?
It is like discretization. But what I want is definition. It is a piecewise approximation of the surface. Tessellation is the piecewise approximation of the surface. It is approximation. Always remember that. ठीक है? It is going to be a piecewise approximation of the surface. अच्छा, अब हमको सरफेस को अप्रोक्सीमेट करना है. इस सरफेस को मुझे अप्रोक्सीमेट करना है. Smallest geometrical entity that can create a surface. Tell me. The smallest geometrical entity that can create a surface. एक पॉइंट है, क्या ये सरफेस बना सकता है?
No, sir.
दो पॉइंट है, उनके बीच में एक लाइन खींचते हैं, क्या ये सरफेस बना सकता है?
No, sir.
Yes, sir.
क्या?
No.
लाइन कब से सरफेस बनाने लगा?
No, sir. No.
हाँ, अब मान लो 3 पॉइंट हैं, पर वो 3 पॉइंट ना कोलिनियर है, ना ही वो कोएक्सियल है, वो एक प्लेन पे लाई करते हैं. इनको जोड़ के मैं एक बनाता हूं ट्राइंगल. क्या ये एक सरफेस बना सकता है?
Yes, sir.
That is why tessellation is also called as triangulation.
Oh, yes.
That is why tessellation is also called as triangulation. So when we say that tessellation is happening, or in your FEM course when you were doing meshing, the surface is going to be approximated by the geometrical entity which can create a surface. So the smallest geometrical entity that can create a surface is a triangle. Okay? So during tessellation, what happens is this object is now going to be divided into triangles. So that you can see in the image also. The image is visible to you, clear? So this is one triangle that you can see. Sorry, this. Okay? So the whole surface is now going to be defined with the help of triangles. So what is tessellation? Tessellation is the piecewise approximation of the surface, and the surface is converted into small triangles so as to minimize the mathematical information that is stored in the original CAD model. That is the whole idea. जो मैथमेटिकल इंफॉर्मेशन है उसको कम करके स्टोर करना ताकि स्टोरेज कैपेसिटी बढ़ जाए. Now, once it has been tessellated, now you get an STL file, and this STL file is transferred onto the machine software. हम लोग जैसे एक सॉफ्टवेयर यूज करते हैं फ्लैश प्रिंट. We use one software called flash print. ठीक है? Now, using the flash print software, we define certain set of process parameters, including layer thickness. Once we define the layer thickness, this complete object is going to be sliced into number of layers. The concept of slicing, other things I will teach you later on in this course. Once the slicing has been done, then comes the next part, the material deposition path. Then the same machine software actually now decides on the deposition path. This is your bed. Wherever the part has to be fabricated, the material will be deposited only there. That is how you reduce wastage. So the material deposition path is defined by the software itself, based on every layer information that has been generated. Once that has been generated, you send the complete information into machine. Now this file is either G3X or .gx. Whatever comes out of this software, these two parts are done in a single software. The output is called as G3X or .gx, and it is sent to the RP system. The RP system creates the physical prototype, and then it is sent for post-processing or finishing according to requirement, and then testing of the prototype. If it is okay, it is the final prototype. If there are drawbacks, you go back to your CAD model. Have you understood the process chain?
Yes, sir.
Have you understood the process chain?
Sir, one doubt is there.
हाँ पूछो.
सर जब SQL फाइल हमने जो जनरेट की थी हमारे CAD मॉडल्स से, इज इट ओनली फॉर RP और कि हम लोग जो ट्रेडिशनल मशीनिंग करते हैं वहां भी हमको रिक्वायरमेंट रहती है? वहां
कोई ऐसी रिक्वायरमेंट नहीं है, बट STL has now become what you can call as a default format also. जो कॉन्सेप्ट मॉडलर्स होते हैं ना, जो मशीन्स में जैसे CNC में भी कई कॉन्सेप्ट मॉडलर्स में अब STL फॉर्मेट एक्सेप्ट करने लगे हैं.
सो तो जो एक्स्ट्रा इंफॉर्मेशन का जो लॉस हो रहा है वो अप्रोक्सीमेशन की वजह से,
हाँ,
अगर मान ट्रेडिशनल मशीनिंग हुई और अगर मैं SQL फाइल में कन्वर्ट नहीं करता तो क्या वो एक्यूरेट नहीं होगा मोर कंपेयर टू?
100% एक्यूरेट होगा, 100% एक्यूरेट होगा आपका.
तो फिर मैं उसको SQL में कन्वर्ट क्यों करूंगा? फिर
STL में इसलिए कन्वर्ट करूंगा क्योंकि अगर मेरा डेटा बहुत ह्यूज होगा तो जो स्लाइसिंग में करूंगा ना, स्लाइसिंग और लेयर डिपोजिशन पाथ, सॉफ्टवेयर बहुत ज्यादा टाइम लेगा उसको प्रोसेस करने के लिए.
ओके, अच्छा सॉफ्टवेयर का इशू है. यस,
ये मैन्युफैक्चरिंग इशू नहीं है, ये सॉफ्टवेयर इश्यूज की वजह से हम करते हैं. और इसमें जो लॉसेस होते हैं वो लॉसेस होते हैं हार्डली 1%. So at the end of the day, I am still getting a 99% accurate part. and that 1% accuracy can always be taken care of later stage.
टॉलरेंसेस भी कंसीडर कर सकते हैं इसको
हम करते हैं वो सब सीखोगे धीरे धीरे करके, अभी तो स्टार्ट हुआ है ना, अभी
Yes.
सीखोगे, सब कुछ सीखोगे ये सब चीज।
Yes.
अच्छा, अब आते हैं बेसिक एडवांटेजेस पे। बेसिक एडवांटेजेस बहुत सिंपल है। बेसिक एडवांटेजेस क्या है? सबसे पहला लीड टाइम रिडक्शन, ठीक है, क्योंकि डिजाइन कॉन्सेप्ट कितना भी कॉम्प्लिकेटेड हो, अगर आप कैड मॉडल बना लिए तो यू आर एबल टू डेवलप दैट ऑन आरपी सिस्टम। It reduces a lot of cost, and the major cost that it reduces is the labor cost. Why? Because if you go into machining systems, you will need a very trained and a specialist machinist whose salary is going to be higher. But in rapid prototyping, except CAD work, all the other things are going to be done by the machine, and you only need an observer who can press the stop button in case of any emergency. Other than that, you don't need anything from the person. Secondly, the quality of the product that comes out in terms of dimensional accuracy and in terms of surface finish is much better as compared to conventional manufacturing system. You save a lot of cost in inspection tooling also. You don't need a lot of tools over here. And the third thing is you can directly create an assembly in additive manufacturing or rapid prototyping, whereas in conventional system, you create all the parts separately and then you assemble. So if you are able to create an assembly, definitely you are reducing the part count. You are reducing the part count. Variety of materials can be used because there are variety of systems which are available. Build time is going to be very fast. Why? Because you can not only you can create an assembly, you can create a part directly. Complex shapes and impossible shapes can very easily be created. Now wastage and rejection is directly related over here. Okay. So wastage and direct rejection rate can be related to the cost, lead time, and part count. Because assembly is going to be made, so wastage and rejection rate is definitely going to come down. So there are many processes, to be very precise. These are some of the processes that we generally see in our day-to-day life or in engineering applications, basically industries also. But there are many other systems also which have been developed, which we will discuss when we go into processes. So the first process that I just want to explain is stereolithography. This was the first process that was commercialized with respect to rapid prototyping, and it was commercialized in around 1988. And it uses a liquid resin. The second process is selective laser sintering. The selective laser sintering was commercialized in around 1992, and it uses powder. Earlier, it was only using polymeric powder. Now, another system which is called as SLM, this is sintering, this is melting. Okay? So that is the difference between SLM and SLS. So this uses metallic powder. SLM uses metallic powder. Then there is another process called FDM. This process is what we have in our labs. FDM process we have in our labs. It was developed in around 1991 and commercialized in around 1993. And this is from Stratasys, a company which was earlier in USA and now it is incorporated in Israel. And this is one of the fastest processes that you will ever see with respect to additive manufacturing. LOM came in around 1995. Sorry, not 1995. It was commercialized in 1995. It was conceptualized in 92-93, and it came into market in 1995. And this uses basically plastic sheets. FDM uses polymeric material also. Polymer, that is ABS. Primarily, it uses ABS. Okay. LOM uses plastic sheets, photo curable plastic sheets, yeah, laser cut plastic sheets. In 3D printing, I explained in the last class also, 3D printing is nothing but a philosophy. So it is basically a class of machines which incorporates all the above mentioned systems. Now, lens is something which is very different. Why? Because this model was conceptualized in around 1999 and it practically came into market in 2002 to 2003. This system uses metallic powder. It was the first RP process which used metallic powders directly, and it can be used to create ceramics and composites also. It can be used to create ceramics and composites also. So these are the most common systems which are used every day. So this is all about today's lecture.